as far as the mechanics and kinematics of the machine is concerned, but that machine may not be giving the performance as per your textile requirement, because the moment you put the textile material on the wood machines which are designed properly based on mechanics and kinematics, it's not may not due to some textile forces is there also when it will be working together the machine and the material. So that's why I just some of the areas where we are working. So I'll try to give you some highlights of that, how textile forces or textile materials can create problems, even though your machine is beautifully designed. So, and at the end of it, I think you'll be able to realize that if you really, if India really, in the true sense, because most of the textile machines, good textile machines are imported. If India really want to design a machine, so there is a amalgamation, there is a need for the amalgamation of knowledge of textile and mechanical engineering. And if we put our knowledge together, then definitely it will be possible to have a better design of our machines, or the machine like the design has been taking place in international level. So I just started the yarn as the topic has given by the professors and the answer. So it's a yarn preparation and weaving. I just select 2-3 machines from yarn preparation, and the particularly subtlest weaving design, machine design is concerned, how we have designed textile point of view, what is the idea in the design of textile point of view. This thing I just like to tell you in brief. So to start with, let us start this together, because winding and not working. So if we carefully look into these two processes, you find that these two processes for if you in a generalized fashion, if you see it, these two processes are more or less similar. There is a package is here. From package you move the yarn in the machine, and ultimately you form some different kind of package. In case of winding, from smaller to bigger one, and in case of working, a bigger chemical package to a parallel package that we call the work beam. So the operation is just like that. We transfer the yarn from one package form to other package form. So yarn is basically, in this case, yarn is basically moving over the different surfaces. So now in brief, basically if I see, so in brief, basically if you see, these are the if it is a winding, then you find that ring bobbin, then guide, tensioner, clearer, stopping device, and winding machine, and we convert smaller into bigger package and remove the objection of front. This is everybody knows it. And this is a machine, one of the best machines ever designed by the textile people. And this is in working while it forms a revolving parallel winding of work from cone package. So here also you see that from clean the control system lead measuring winding drum and direct. There are two types of machines are there, drum and beam winding machine. So this is a drum winding machine where directly winding it, and yarn comes through different surfaces and wrapped on a winding surface, and here also here the yarns are coming from over different surfaces and reached to here. So now I just in this process I will take up entirely different problems as compared to commonly textile people used to concern on that. So that problem is here. So environmental problem in these particular two machines where it is running. So this is just a caption, not much relevance with this particular presentation, just a caption for environment. So I'll come here in these two machines, whenever it's moving, if you see that this machine generates a lot of fly, particularly if you use the process cotton yarns. So you'll find there are a lot of fly generating on during the process of the transformation from one package to another package. So this fly is basically what the fly is basically how we define a fly. Fly is basically fiber that fly out into the atmosphere during the process. It affects the environment as well as the quality of air, and this can cause basically the most important. It can cause the health hazard of human, particularly those who are susceptible to respiratory illness. So this is a nowadays people are very much concerned about the working environment. So irrespective of the best machine you are using it, and if you work with the spun yarn, cotton spun yarn, the fly will be inevitable, and the creation of health hazard will be also inevitable in that room where it is working. So I just try to give you some idea that what are these fly means and what are its characterization. So if you just characterize the fly which is flying in the room, it can be around 25 to 26% fibers, which is of 1 millimeter length, 41% of 3 millimeter, 21% of 5 millimeters, and 12% of variable fiber. So if you see the distribution of the flies, which are basically just like the colloidal suspension in liquid, in the air, basically they are in the suspended form. So it can be 1 millimeter, major 3 millimeter fibers will be in the suspended form, and it can be 1 to 5 or more, slightly more than 12%, slightly more than 5 millimeters. So these are the fibers which will be suspended in once it is running on the machine, comes out from the machine and comes out from the yard during the running of machine and creates a huge amount of problem in our environment. So now after this, now let's try to see that what are the possible reasons that why these flies are generated during the process of transmission from your one package to another package. So you see that there are mechanism to generate fly. So there are two areas which are basically mainly are responsible for creation of fly. One is that so here is the delta or triangular type zone has created when you pick up the yarn from the surface of package, and where you can find it from here. The entangled mass of fibers in the entangled fibers are there. So whenever we just pulled out the yarn from the surface of the package, this particular zone you find there are entanglement fibers are there, and we will rip apart and comes out from the yarn surface and will produce a fly. The other is that the yarn is having hairiness in it. So during its movement from one package to another package, it has traveled a long path. And during that path, it has come across, there are a number of different type of guides or elements over which it is passing. So if you see this, the next figure, you can see that the fibers which is projected from the yarn surface will strike the guide. So the moment it strikes the guide, or it will rub over the surface of the guide. So this free end of the fibers will having the free end of the fibers will be through this free end. Their force will be exerted on the free ends. So if your inside force is holding force is less than this force, so then there is a possibility of it comes out. Or you can repeatedly, if it strikes in, so number of guides elements are there. If it repeatedly strikes the guide, so due to bending and unbending, so after some time it can be breaks and comes out as a fly. So these are the major reasons why the fly is generated from that. One is from the contact points between the take-up points from your package and the yarn surface and the entanglement fibers. And the other is that whenever fibers
हेलो बड़े सर।
हेलो।
हाँ बड़े सर।
हाँ।
तो वॉइस नहीं आ रहा है आई थिंक।
अरे समझ नहीं आ रहा है। समझ में बात कर रही है। Good afternoon to all the participants. Be patient. Actually, there's a technical issue in the Jalandhar because of maybe the rain issue. Network is not proper, and our one of the organizer who is in contact with Professor Subrata Ghosh. He's hello.
Hello.
Our one of the organizer is in contact with Professor Subrata Ghosh, and soon I think we can able to connect him. Till that, I welcome Parikh sir again, and we can have that the discussion with him regarding the
Hello.
Regarding the Surat textile industry. Sir, if you can able to share your camera, it will be good. At least participant can able to see your camera yourself.
Camera. Ah, yes.
Yeah.
Yeah.
Once again, come back to the Surat textile industry. Sir, you're talking about cleaning and washing is not an issue with the saris and dress material, right? Which is made by the man-made fabric. But when you are going for the market, the range is from 100, normally 100 to 100. I am not having exactly idea, but it is in some thousands. So on what basis this cost is going to be decided, and while purchasing, what we have to think about it, what we have to see.
Generally, the price of the sari or dress material is based on value addition which is being done. So generally, plain dyed sari are cheapest among all this, and which is in the range of say 400 rupees or something like that. Printed sari would cost you more than 600 rupees, around 600 700 rupees, a good quality, I mean. And then if you go for the value addition, if you want embroidered, then the extent of value addition will decide the price. So heavily embroidered and sari with work will cost you more than 1500. It might go beyond say 2000 or 3000 rupees a piece. So ultimately, it is the value addition which decide the price actually in Surat. Otherwise, dyed and printed sari plain are not that costly. It is in the reasonable range. Now, depending upon the brand, they may ask for more price, but otherwise, all these job work oriented people, in their retail outlet, they go for this. It is between 400 to 800 dyed or printed. So that is the case.
So you are again touched the point difference between the branded and normal sari, whatever is coming over here. So what is the difference between branded saris and normally whatever available without brand?
Branded sarees, these are, I mean, they are having very good quality system in place. So even if they are purchasing gray fabric from the weavers, they ensure that it's a fabric of very good quality. And even if they go for job work, generally branded people, they have got their own weaving house as well as printing house and value addition. So everything they do by themselves. And that is why there is a very good control over the entire process, and the product available is having very good quality, and therefore they can ask for that. The brand is for that because the quality assurance is there.
Achha. So basically, I think the quality, how the quality is going to make difference in our day-to-day use. Can we give the importance to the quality control, whatever is there?
I think the main speaker is now, I think,
Yeah,
visible.
just 1 minute, last question, we can take it up and we can start.
The variety actually, branded people, they care about their product, and you know, if any branded sari is there in the market, what job work people will do, they will reduce their quality by decreasing reed and peak, and the entire structure of the fabric is, I mean, disturbed, and that is how quality affects. I mean, whereas in a branded, you are assured of the quality of fabric as well as the processing. So that's the final product is also having very good quality.
Okay, nice for information. I think time to time we may have some questions to you because fabric is not just a need, but it is present personality, reflecting the personality. Okay, our speaker Subrata Ghosh is come back again. So I request sir to start his presentation from where he left. And hopefully the network issue is resolved now. Sir, you can start. You're talking about the mechanism of reply generation. So from there you can start. एक मिनट हाँ सर.
Hello. Now is it all right? Hello.
Hello, हाँ sir.
So after this slide, this was the last slide I was talking at that time. So now from here let us move on to the next slide. Now So see that here, this particular slide, just I want to show you that the virgin fibers and the broken fibers, which is basically as a fly collected from different surfaces, and how it looks like. So just an idea that how fiber fly can be, just a look on that. So this is the how they here from a core yarn structure, how the fibers can be formed in hairs, and ultimately hairs have been liberated as a fly. So the possibilities here that here can be three possibilities. You can see it from the one, where the hair fiber is at the hair is outside and inside it is a locked well within the different fiber contact surface. The second one, where the fiber is at the surface of the earth, so freely just on the yarn surface. And the third one is the fiber is outside, partly outside and partly inside. The locking is relatively less. So these are the possible three, four types of lockings are there, and these are the possible lockings out of these. So these are the possibility as far as when we think for applying forces on it. So if you see that there is a fiber which is both as a hair having from the yarn structure to the outside and inside every structure. Now if it can, one of the possibilities there FH is the forces through which it is bind inside the structure. FF is the force which is acting outside due to friction and pulling out forces, and FB is the breaking strength of the fiber. Now, these three forces will decide a particular fiber, which is in the form of a hair, whether it will go with the yarn, or it will break somewhere, or it will come out from the structure of the yarn. So now you see that there are three possibilities. So when FP less than FB and FP less than FH, that means neither the force is high enough to pull it out from the core structure, nor the fiber is having the force is so much that it will break the fiber at its weakest point. So if that is happened, then the fiber will go with the now if there is a possibility of when your inside structural force is very high, but if I pull it by the certain amount of forces, but the breaking strength of the fiber is relatively weak, so it will break at the weakest point and it will come out as a fly. Or there is a possibility when the fiber, the internal forces which are is binding is less, and the external forces acting on the movement of yarn over different surfaces, then the fiber will come out or liberated as a fly with a larger length. So the first condition we know that the fiber will, the hair will remain on the yarn structure. The second condition is that fiber will break and the fiber will generate a very small fly length, very small. And the third condition is that when a fiber comes out from the yarn structure as a longer length of the fly. So these are the three possibilities for which is there in your fly generation from your machine. It can be working or it can be winding. Both the cases have yarn, we have to move on different surfaces. So it can be generated very fast, short length fiber, or it can be a longer length fiber. But both of them will be whatever may be the fiber, it will be length in the range of fiber slightly more than 5 millimeter to 1 millimeter. So it's a fly, and it will create hazards in the room. The people who are working on that, and also if you go outside the room, then it will create hazards to people around surrounding the area. So one problem is that now you have to take the only possibility that you have to redesign your machines. So although there are in the machine we have some facilities are there for collection of fly are there, may not be good enough to collect the total generated fly. So there are another possibility that there we can think for higher fiber having a higher load extension value so that it will not break during the process. And the third possibility is that the in addition to these two, we have to think for an environment of a room where there is a collection device from the whole environment. If we can collect the flies, and then that flies may not be any useful for spinner or spinning person because it is less than 10 millimeters flies are there, so may not be useful for the spinners. But these flies can be very reusable, even though it will create an environmental problem. If you can collect them, there is a possibility of reusable as a fiber of absorbent material, which is a medical textile we call as a absorbent materials. The short fibers, very short fibers, are used for manufacturing hygiene product. So primary characteristics will be of high absorbency behavior. So if we can modify those cotton fibers with some concept, some kind of surface modification of those short fibers and bring into a different form. So those fibers which are waste and polluting our atmosphere, we can collect it and use as a absorbent material. So there are a few possibilities that there. So it has to be searched on, and all depends on that how we can look into the problem of this particular two machines. So now let's move on to next one. Sizing. This is a machine which has been taught to the textile students in a way. I try to say something in a different way from the angle of mechanical engineering people and partly from the textile, so that people can look into this particular machine in a slightly different way as compared to the textile people used to look into this machine. So let's first start with that. Why do we need sizing? So all of you know that from what we the sizing, drying, and reversing, these are the process how we convert it. But as we said, the applications of protective coating on the work yarn to minimize the breakage during weaving. So that's the whole aim. And why we need that kind of protection? I just give you an example here. Suppose in our batteries there is a yarn and cloth thread. In between them there is a length of 1.5 meter, and every yarn length will be there. Now at a particular point at the batteries, so to reach on the cloth thread, it takes how much time or how much number of loading and unloading cycle. If the machine RPM is 500 and 6 centimeter is 20, so at least that particular yarn which is at the point at any moment at that waist to reach in the cloth thread, it has to be 3,000 times loading and unloading cycles. So it has to withstand at least 3,000 times loading and unloading cycle. And that's the reason why we go for protection of the protective coating on the cloth yarn, because in our experimental in one of our experiments at NITJ, we have seen that if you take a raw yarn and try to run on a weaving machine, so that raw yarn cannot withstand even 400 to 500 cycles of loading and unloading cycles in the actual process. In the actual machine, it cannot raw yarn without sizing a yarn just to try to see the experimental how much loading cycle, loading unloading cycles that particular yarn can withstand in the weaving machine. So we have seen that it can't take more than 400, 500 cycles. So 400 and 500 after cycles, the trend is almost falling to zero. Whereas in actual manufacturing, tentatively, it will have to go under 3,000 cycles. So, and that's why we need watt sizing, and that's conceptually what is the reason for why you need it. 3000 is too much cycles. It has to stand at a particular point of the yarn during moving, and that's the need how we do. That's the need of sizing. Now, the sizing is basically this is a big size machine, and this is one of the most energy consuming machine as far as the textile is concerned. So reason is very simple, because here the whole yarn is in wet condition. So we apply size in wet condition totally in saturated form in a wet condition 100%, and then when it hits to the other end, it should be totally dry form, so that from one end to other end when it will use, so it will be naturally the yarn will be dry, so that the whole process a huge amount of energy is used, and this is one of the machine where we are using maximum energy. So if we can see that this particular sizing machine can be a fit case for mass balance and energy balance equations, which are very normally whenever we try to go for a unit operation particular process, and this particular sizing is basically a fit case for mass balance and energy balance. Now you see that as far as the mass balance is concerned, what we are giving input yarn is moisture, and the other input is the sizing gradient, that is the input which is there in the size box, and then it comes to dryer. The output is the size yarn, and the output is the moisture which comes out from the process. So it's a clear case of mass balance equation, mass balance condition. So we have mass M1 and M2 just put together inside the box. So that means mass M1 and M2 joined together. Then at the dryer, there is a mass coming out from the evaporation bar M2, and there is a side yarn comes as a mass M4. So this is the same case for mass balance as far as the machine is concerned. And you can see the energy balance of this in the dryer. We apply the steam heat by having a steam. So if you are applying a steam here, so steam will be used by three-fold steam, which is supplying it in the dryer. So it can hit the wet yarn. So it's a Q4, which is heat is supplied to the dryer, and subject of steam is there, and the condensed water is there. So this is the case of energy balance. So this particular machine, which is one of the most energy consuming machines, and having a lot of is one of the most crucial processes as far as the is concerned. So if we can analyze it based on mass balance and energy balance, then definitely this machine we can use better optimally from this particular process. So it's a mass balance M1 plus M2 and M2 plus M4, and M1, M2 having a lot of parameters, textile and machine process parameters, and MC and M4 also. Similarly here, energy balance Q1 we are supplying it, it's Q2 is for heating, drying off wet one, Q2 and Q4 is exhaust from there. So that's an energy balance equation. So we can do this machine in a slightly different way as compared to that. Just I'm giving you 6,000. If we have a 6,000 ends and 12.5% pickup, then possible just a case taken from the typical textbook. It's a 17.7 kg conditioned yarn, which is dry yarn is this having moisture, and 19.78 kg side phase having dry side is 2.74 and 17.31 kg of water. So now when it dried out, the size here is 20.37 kg dried out is there, and the water which is evaporated is 17.717 kg of water to be evaporated from it. So that's a huge amount of water is need to be evaporated in this machine, the running machine itself, from input to output end, and that's the energy we are using. That's the amount of energy we're using to evaporate your water from here. So this is a equation which gives evaporation per minute. All the units are in unit system. So what means the speed of the machine, ACB site, percentage site applied, and then is the count of your account and C site loss concentration. So in terms of these parameters, evaporation rate of a machine is basically you can calculate from this. So just this is just what I want to. This is the last slide in this sliding with removal water from solid. So drying of work which takes maximum energy in the process basically. So removal water from solid. There are usually there are two ways to remove the water from solid. So water can be removed mechanically by applying pressure or by centrifuge. There are two techniques usually used in the industry, either mechanically by applying pressure on it or by centrifuge or by thermal vaporization. So we all know that if you want to thermally use it, then the cost of energy will be much higher. So that's why here also in this machine we try to remove as much as water is possible by mechanically, and then it apply thermals on it. So a machine, siding machine. So around that's why now the modern siding machine has been developed high pressure in the screening. The pressure is very high in the range of more than 1.5 to 10 kilonewton in this range. You apply force on the beneath 1.5 to 10 kilonewton. So it's basically due to that excessive pressure as water can mechanically remove it due to high pressure screening. Then that particular machine we are printed with the high pressure screening. We can save energy around 20 to 22% of the energy in the process in this particular process. So that's a possibility that if we can do a design conventional machine slightly in this area so that we can go for a high pressure and mechanically extract as much as the amount of water is possible, and so that thermal vaporization will be lower down and you are having a huge amount of energy saving possibility will be there. So that is another possibility as far as your sizing is concerned. So that's all whatever I thought of talking about this particular machine. Now I'm talking on the machine which is design machine, that is your surface machine, design and development of surface machine. So in this particular, before moving into this area, so I just want to say something about this, that why you feel there is a need to develop a surface machine. So it has been driven by a number of factors. It's not a single factor which is called this particular development of design and development of this particular machine. There are a number of factors of here which is responsible for driving the design and development of this machine. Now let's try the factors which are historical background behind the development of this machine. So one is the population growth. This high growth of population always need a larger amount of clothing. So rising of GDP, as the GDP of the worldwide, every country is improving, so they need a better quality product. So development of new fiber and uses. So whenever the new fibers are there, so you need something different kind of machines to handle those fibers. Then you find also the progress in mechanical, electronics, and computer engineering. So all of you know that these machines are printed with all kinds of gadgets in their design. And of course, there is a demand and standards of end user. There is a demand from the end users, and there is standards of the goods are increasing. So automatically the demands will be different. So in order to cater their demands, we always need a better and better. So that's the reason the factors which drives the development of the machine. So population is one, the rising GDP, the new fiber, you need a different kind of machine to handle those fibers. So there is a tremendous development in mechanical electronics and computers. And of course, if people wants, then you have to go for it. If the people doesn't want, then there is no need for going such kind of things. Now, if there is a demand from people, the industry is always going towards that. Now, just I'll give you one typical example that. So I think that this will be an interesting how the consumption pattern all over the world. So how much amount of cloth is basically consumed worldwide. So per head consumption, this is just here. So North America is basically one of the highest consumers. So even 1917, they are in the range of 10 to 25, 20 in the range of 10 to 11 kg per head consumption. North America, Western Europe is a country who are having the highest consumption as far as the textile is concerned per capita consumption. If you see that the Africa, South America, and Asia. So if you talk about the consumption is less than 4 kg, Africa is around 1 kg per capita consumption of fabric is here. So that means if the changes are there in their GDP and the level of Africa, Asia, and South America is improved, so automatically the per capita consumption of fabric will be increased and automatically demand will be higher and higher. So you need to be high productive machines if they are required, and automatically the machine manufacturer are driving towards that so that they can go for design a new kind of machinery. Now see, because of that, newer kind of how this newer kind of machine has been designed. What is the problem of a conventional machine, which is called certainly even in India, even today, the maximum amount of fabric is produced by this machine, certainly. So even today we are manufacturing large amount of fabric in Satilum. So forget about the Satil swimming. So we are having there some amounts, but what is the problem of Satilum? So that it leads to the development of Satil swimming. So the first problem is that we just so to insert a few milligram, a full length of weft is working around a few milligram. So just for the insertion of few milligram weft, every time we accelerate and deaccelerate a huge amount of mass, that is 500 grams. So this is the first problem of the machine. So just to insert a few milligram of weft, we are accelerating and deaccelerating 500 grams material. So given that there are a lot of noise and so noise is creating soft and noise is creating on the machine vibration, and taking system under huge amount of wear and tear in this. So it creates the problems from noise to wear and tear to a technical problem of just insert a few milligram where we are inserting a 500 accelerate and deaccelerate 500 grams of mass. So then what can be the possibility? So in order to design a high-speed machine, the basic science is here. All the machines which are designed based on the basic science is here. So we want to increase the insertion rate, that is, we calculate the capability of any machine in terms of insertion rate. And this weft insertion rate of the machine is basically equals to B into theta divided by 6 into 1 plus L by R. This is a major summary. So that's how we calculate the capabilities of the production rate or capabilities of a within machine. Now, this velocity of weft insertion media per second, theta is degree available for the passage of your weft, and L is the effective length of weft carrier, R is the width of the machine. So this particular equation, now everything, all the machines are left in machine that can be RJ or RJ or projectile. All the three machines have been developed from the basic fundamentals of this equation. Now see that from here you can see for given L and R, the ratio is if the R reading is high, the L by R ratio is almost negligible. So then the weft insertion rate is proportional to B and theta. Well, B being the velocity of the weft inserting media, and theta is the number of degrees available. So basically, if we want to insert a weft at higher rate, so we have the two parameters. Either we have to increase V or we have to increase theta. But as I say that in case of our second loading, so we have to accelerate increase the V is very almost impossible to reach the maximum limit. So I will be giving you an example. So V is almost impossible in our conventional machine and also theta because of the design. So that's why we need a total design change as far as the machine is concerned, and that is what has been done in ERJ or ERJ and so dismantle the drive system, which in our conventional machine we have used the drives to centrally to a crankshaft, and from there all drives, we picked up all drives. So here, in order to achieve V and theta, we just dismantle the drives, central drives, and the designer has brought individual drive to the machines, different element. So for given each of the loom and then the load carrier insertion rate is varying in V and theta, so we have to look into that how we can include V and theta. So I just give you that how the insertion rate of different loom machine is different in terms of their design. Certain load, so these maximum speed of 13.75 meters per minute, meters per second, and theta is 135 degrees. And with these variables, the insertion rate is to 245 meters per minute. As projectile, the projectiles, the vapor speed is around 30 meters per second, and theta is around 255 degrees. So work insertion rate is around 1150 to 1200 meters per minute. Then if you go to here we have the velocity of weft is further increased from 30 meters per second to 40 meters per second. But as the work insertion rate is very high, so you reduce theta within 10 seconds, 110 degrees. So work insertion rate is 1600 meters per minute. So this is one of the highest insertion rate. And here V is around 16 meters per second, and theta available for this machine is around 330 degrees. So this theta is depending upon the specific design of the insertion of this material. That's why it can be 255 for projectile, 330 for replier, and theta 110 for your Z. And in combining the velocity and theta angle available, we get to the weft insertion rate of different machines. So if you see that, that's how our this increase linearly or almost not linear, not linear. It's a certain, it can be 245 meters per minute. It appears in the range of 800 to 1000 meters, 800 meters per minute. Projectile 1200 meters per minute, and here you go 1600 meters per minute. And the basic philosophy for their development is only on 2 years. They are taking care of 2 years. That means if your weft insertion media velocity and your angle available, so that it can be set for a longer time or shorter time depending upon the design requirement. So these are the three for best loading machine ever designed. So I'm probably out of these three machines. I give you one information to all of you. So if you see the market, if you see in the market, commercial market, worldwide, there are so many manufacturers as far as your jet and repair is concerned. There are so many numbers as far as the jet and repair is concerned. So the multiple commercially available manufacturers are there, and their machining is comparative to each other. But if it comes in the projectile, you'll find that the projectile is a unique machine. No other manufacturer is manufacturing this particular machine. This is manufactured by only Brothers of Switzerland. So and beauty of this machine is here in this particular diagram what I have shown here. So this beauty of the machine is basically the thinking mechanism of this projectile machine. So what's the specialty of this thinking mechanism here? So this particular is really a mechanical engineering marvel as far as the thinking mechanism is concerned. So we have a torsion bar here. So we twisted that bar by using a cam and we store the energy momentarily, and suddenly we release the energy, and that energy is used to accelerate the work yarn carrier that is called drift bar. So this is a unique machine all over the world. Nobody else is manufactured other than Switzerland. So and its uniqueness is here in the torsion bar fitting mechanism that is twisted and we store the energy inside it, and suddenly we release the energy as and when we need it. So that's the beauty of this particular machine. So in mathematical terms, this total energy stored in the bar is C theta square by so C is the torsionality of the bar, J is the Coulomb momentum inertia, which is function of the group, and theta is the angle of twist, and L is the twisting moment. So you can see that the stored energy in the bar can be changed by using the diameter of the bar, using twisting angle of the bar, and length of the bar. Those all three possibilities appear in our fluid carrying machine. Either it can be theta or it can be D diameter. If you need the energy, high energy, then you can change the theta slightly. You can change the diameter of the bar, or you can change the damping length L of the bar. So this is the possibility. And that particular energy which is stored could be transferred to the driver and in the form of the kinetic energy mv square. So this is the energy equations for the thinking mechanism of this beautiful machine. And I'm telling you, this is one of the finest machine designed and one of the most successful commercial machine. But when we calculate the energy conversion of this particular machine, we will be astonished that out of the total stored energy, only 14 to 15% of the energy which is stored is used by the grouper, and rest of the energy is basically dissipated as a lost energy. So even in this finest machine, the energy conversion is basically here in the picking area is 14 to 15% of the energy conversion is here. So this is how this is an interesting historical figure diagram from 1900 to 1980s. You know that the one side we are showing it that how the mass of wet material, that means from certain 400 grams now it is reducing 40 grams, we are taking almost negligible weight. So how the mass of the wave insertion rate is reducing with time and the design of different kind of machines. So for the conventional loom, 40 grams carrier weight, projectile 400 grams carrier weight, conventional loom, projectile 40 grams per weight, and they almost negligible weight as far as the carrier is concerned. And here in other using energy consumption, So if you see it here, energy consumption, as far as the energy consumption is concerned, the projectile machine is the one of the machines which is the lowest energy consumptions as far as projectile is concerned. And ELT is the highest amount of energy consumption, and then regular and conventional will have similar level. So I can as far as the energy is required, energy is concerned, it will be the lowest amount of out of this machine, right? So I'll be before finishing it up, I just give you the another problem of these all these machines. Good machines, with all three machines are subject to the design is concerned. If you see their insertion rate is very high as compared to 1100 to 1200, 1000, 1600. So they are the fittest commercial machine as far as the production rate is concerned. So that's why it is almost all the three kinds of machines are well acceptable in the industry. But even though these machines are designed today, I'll tell you that. So there is some problems with these machines are also, and that is what basically I'll tell you. So how to handle these machines, and in order to handle this machine, you have to have a very good knowledge on textile forces. So these machines are good, but the moment you put the yarn on it, so it starts creating a lot of problems. Whether it can be any kind of machine, you are good to design as well. So one of the textile problems are there as far as this machine is concerned, and what are the source of that problem? And you know that the efficiency of this machine is depend mainly on the end breadths. That means a yarn which is from warping to the cloth fill is here, and the weaving machine is working here. So that creates a whole lot of problem as far as the yarn is concerned. And I'm telling you, interestingly, so whether the thread will break or not, it will decide upon it will depend upon the what is the forces basically, what is the tension developed in the yarn during its 360-degree process. And that tension is highest in the zone where your elements are moving. That means here the moving element, it is 360 degrees, it is always changing its geometrical position. So due to changing geometrical positions of the heel, it is always changing from 0 to 360 degrees, always changing its geometrical position. Due to changing this geometrical position of the heel, what happened? The tension always be fluctuating in the yarn, and the moment the yarn tension will be exceeding the breaking strength of the yarn will break and the machine will stop. The whole thing has gone. And that's why the yarn strength, what is the tension developed in the running area? And as I said, that this running area, the geometry is always changing, so it is almost impossible to install any tension measuring devices here. So we only have an idea of what can be the tension of the yarn by using a tension devices as mentioned at red color. So that is the area where we can only have a tension measuring devices to have some feel what can be the tension developed in this particular area. So if you see that particular area, that's the only area where we can have some kind of measurement is possible, and beyond that it is almost impossible. Because this is a 360 degree, it is continuously running, changing its position. So geometrical configuration will always change here. So only the other way is that if you can do a mathematical model of the whole process. So that means moving of yarn from your back race to the cloth thread. If you can do a mathematical model of this whole process, running process from 0 to 360 degree, then we can have a clear picture that what is happening on every degree of rotation of this particular machine, and as far as the tension on this particular area is concerned, tension on this one is concerned. So keeping this thing in mind, actually I just give you we have already done a mathematical model of conventional machine, So which is published already in a referred journal. So how to find out a tension in this continuous geometrical changing area from starting from the whole mathematical model of the whole process we have done in our and it is already published that how young tension is changing at this particular zone where almost impossible to measure the tension value. So I just end up with this particular diagram. So this is how the tension is there. Suddenly the tension, yarn tension is changing with this profile, work yarn tension changing this profile. So usually, usually while we are measuring at this point, tension measuring device are fitted. Here you'll find that the tension is around 40, 50 to 100 grams, around 100 grams. A tension measuring device can be mounted. But when from our mathematical analysis, we found that this active area near shade and read, the yarn tension can go up to 2.5 to 3.5 times higher than that of your whatever the tension at the tension measuring device, where you can locate the tension measure. That means if it is a 280 to 100 grams, it can be go up to 200 to 300 and 350 grams of tension. Now, if your yarn is having strength less than 300 grams, then it will definitely break. So that's why the tension which we can see at the tension measuring device, but in the active area, where the continuous change in geometries of the process is continuously changing through 360. So from mathematical model, we predicted that here the tension is 2.5 to 3.5 times higher than that of that stationary zone, which is indicated here. So if your yarn tension is high, if your yarn tension rise so high and yarn is incapable of handling such strength, or your yarn weak point, your yarn weak points is having a strength less than that, your yarn weakest point strength is less than this value. So definitely you will expect a thread breaks, and if the thread breaks, then definitely this machine will be a disaster for that industry. If it will break every alternate minutes, so then these high-speed machines are basically disasters for that industries who are like to run these machines, because these machines should be able to run it continuously without any stoppage. Then you get the benefits of higher pixels. And if it breaks, because say 6,000, 8,000 ends are there, any one breaks, and that will be good enough for stopping for around 1 minute. So that's the mathematical part of this analysis. Textile forces here. So just a machine, with all machine are do as far as this, as far as the design of mechanical concept. But if you don't analyze the textile forces, so definitely it will be creating problems. But as far as projectile, repair, and this particular mathematical analysis, we have not done it. We have done only for subtle leveling. So this is wide open. Anybody can do the mathematical modeling of the weaving process, so that they can plot the yarn tension profile, what yarn tension profile from 0 to 360-degree rotation of the machine. I think this gives you an idea about how this weaving machine has been designed. So I am at the end. So this will be my last slide. How to choose a machine commercially, jade, rapier, projectile. These are, most of you know it, but even then, as I am telling you, I just summarize it in a way. So I think for me, I'll go for a jade. If you want to print fabric in bulk form, huge amount of land, you want to produce it, and without minimum design possibility wanted, then definitely the best machine nowadays is your Piaget. And if you want a color mixing, it's a huge amount of color mixing here in your design. then definitely you should be always refer by color mixing and also different kind of wet. It can handle the rapier. One of the biggest advantage that it can handle any any kind of wet. This machine can handle a different kind of wet easier, but airjet cannot do it basically. It cannot handle any kind of wet. So rapier has advantage for the mixing, color mixing of design, and the wet is concerned. The variety of wet rapier. And since a projectile, regular projectile machine usually it should go for a very large meat, 5.4 meter diameter. Even it can go up to about 5 meter diameter, 5 meter width. So if you want to go for a 5 meter width, more than 5 meter width, then definitely projectile will be the best machine for high weight, because you can go for this machine without much reduction of loss insertion rate or RPM of the machine. So it can go up to very large with this machine projectile without much problems. And that's all three machines, and that's why all the three machines coexist in commercial arena even today, because they have their own advantages and disadvantages and area of use, and you have to choose right kind of machines so that you can work on that for your need. So which machine can be fit into your commercial use. So at the end, at the end, I'll tell you that. So these textile machines, if we want to design, and most of the machine, whatever I have shown it to you, running in almost all Indian good industries, they are all foreign made. So if you in India, we want to design it. So there is a need, I think there is an amalgamation of knowledge between your textile and the mechanical engineering. If we have the amalgamation of knowledge of textile and mechanical engineering put together, then maybe in future we'll be able to design some of the machines like the one which will see and which are machines which are designed by international level by the different manufacturer. With this, thanks to all of you, and thanks to the mechanical engineering department NIT Surat, and thanks to Professor Puri and Mikey and Mr. Roy for giving me an opportunity to speak in front of all of you. Thank you very much.
Thank you very much, sir, for your lecture and efforts whatever you put for the preparation of this lecture. I think it is now 3:30 exactly. If any question is there to the sir, what I feel is we can share the details of the sir, and you can give the you can send the directly mail to the sir. He is very kind enough to answer your questions. Dr. Maiti.
Hello.
Sir, if you just give the concluding remark.
So first of all, I should thank Professor Ghosh for giving a nice lecture. So as a continuation from yesterday what we have seen that how the fibers are collected either from nature or from petroleum product, and how it's spin into a yarn. Now today what we have seen that from that yarn, how this yarn is placed in such a way so that we get the fabric. Now that fabric before we weave the fabric, it has go to several process like winding, unwinding, warping, then sizing and all these things. Why this process is important, that also very well explained by Professor Ghosh, like how the hairiness is generated and how it is removed, and after that to remove how this size is playing the role, and this how the drying, what is the kinetic aspect of these things, what is the mathematical modeling of those drying process and all these things. And finally, when it comes to weaving, how different types of weaving machines play in the role, and how these machines have been selected, what is the production rate. So all these things is very nicely explained by Professor Ghosh. And once again, thank Professor Ghosh. Now it's Professor Bade.
Thank you, sir, for the concluding the remark. I think we can now again thanks Professor Subrata Ghosh, sir, and we will now leave the meeting because 4 o'clock we have to join another session. The next session is going to be a wonderful session. This is also going to be conducted by one of the renowned Professor Professor B.S. Butola. It's I think completed the MTech and PhD from IIT Delhi. PhD from IIT Delhi. So it is also a good opportunity to listen Professor Butola, sir. And hopefully the issue whatever we are getting because of the network, we are trying to resolve it soon. And the next lecture, I think there's no going to be any issue. All right. I declare this lecture as complete. Okay. Thank you, Subrata, sir. Thank you, sir. Dr. Kalyankar, sir, do you want to say something?
Yes, sir.
Yes,
Can
sir.
we end this session?
Yeah, you can end.
Okay. Thank you.
Okay, sir. Sir.